So today's video, we're going to be looking at the idea of a relation and then also the concept of domain and range of a relation. So again, it's really definitional and it relies a lot on the notation that we talked about yesterday around sets. And it's really important to get these things right so that you can accurately communicate the mathematics. Okay, it doesn't really matter how well you understand the concept of domain and range and all those sorts of things that we're going to talk about, but if you can't accurately use the correct notation to be able to describe those things, then it won't really be worth any marks. So again, it's really important to focus on getting these things right. Okay, so the technical definition of a relation is that it is a set of ordered pairs. So a set, we talked about yesterday, being a collection of things, and this is a collection of ordered pairs. Now, an ordered pair is a fancy way of saying coordinates. So a relation is a set of coordinates. So basically, anything that we could draw on the Cartesian plane, whether that's a series of dots, whether that's a parabola, whether that's a line, whether that's a squiggle, whether that's a smiley face, anything that we can draw on the Cartesian plane is a set of coordinates, okay? In the case of the parabola and the line and possibly the squiggle, depending on how complicated the squiggle is, we could describe all of those points using a rule. In other instances, we won't be able to describe all of the points using a rule, and we might just list them as a series of points. So for example, this would be a relation. It's a set of 4 points, okay? More commonly though, we would have a rule. So here's a set. Remember we talked about this notation yesterday. So it's a set that's made up of coordinates of the form x comma y, such that the y value is equal to 2 times the x value squared plus 1. So this is a set of all of the points that lie on this curve, which is a parabola. Okay, every single point that lies on that parabola. So infinitely many points in that set, but they all have a common theme. Okay, so that's a relation. Any set of ordered pairs is a relation, so anything you could draw on the Cartesian plane. Okay, so then we talk about the domain and the range of a relation. So the domain of a relation is the set of all of the first elements in the ordered pairs. So that's the x coordinates, the x values. It's the set of all of the x values that that relation exists for. And so, for example, if we have our relation that's made up of the 4 points, then the domain of that relation is the set of all the x values, -1, 2, 5, and 8, which is this set here. The range of a relation is the set of all of the second elements in the ordered pairs. So second elements in ordered pairs are y coordinates. So for example, in our relation that's made up of 4 distinct pairs, our range is made up of the 4 y values. Now again, conventionally in listing that set of numbers, we would list those numbers in order. So -6, 1, 3, and 4 is those y values in order. Okay. Let's just, before we move on to the example, let's just have a think about this relation that we defined up here. Let me come over here. So our relation is the set of ordered pairs or coordinates where the y value is equal to 2 times the x value squared plus 1. Okay, so if we think graphically about what that looks like, that's the parabola. That's a parabola dilated by 2 from the x-axis and translated up by 1. So something like that. Okay, so in thinking about the domain, now in terms of notation when we talk about domain, we write dom as shorthand for domain and ran as shorthand for range. If we're talking about the domain of a function called f, we would write dom of f or ran of f. If we're talking about the domain of a function called g, we would write dom of g, ran of g, domain of g, range of g. Okay. In this instance, our function doesn't have a name, so I'm just going to write dom and ran for domain and range. The other thing to be clear about here when we write this is domain is a set. So when we write domain equals, whatever goes over here must be a set, and so therefore has to adhere to all our set notation conventions. Okay. Similarly for the range is a set of numbers. So that we must adhere to all our conventions. The most efficient way to describe a set of numbers is usually using interval notation, or we might make use of our R plus, those sorts of things as well. We probably wouldn't use inequality symbols much when referring to a domain and a range, okay? Alright, so let's talk about the domain and range of this. So domain being all of the x values that this function exists for. So if you think about this graph, okay, I'm only looking at a piece of it here, but this graph goes on and on and on forever, okay? When x equals 10 billion, I'm going to be able to calculate the y value. Sorry, there's more zeros than that, but when x is huge, I'm going to be able to calculate the y value. Similarly, when x is negative 10 billion, I'm going to be able to calculate a y value, which will also be huge, okay? So this graph exists for all x values. It doesn't stop anywhere, it keeps going. So when we talk about every single possible number, we have a very quick shorthand for that, are all real numbers. Can I note here, and I'll mention this will come up in the example, but we don't write the interval from negative infinity to infinity. If you want to write that, write R, okay? So whilst it's not technically incorrect, it is not conventionally how we would refer to all the real numbers, as being all the numbers that go from negative infinity up to positive infinity. We would just use R. Okay, then we think about the range, so all the y values for which this graph exists, okay? So this graph doesn't exist anywhere down here. There's no parabola happening down here, okay? It only exists at y equals 1, and then for all the y values above that, okay? So in terms of the range, it's an interval that starts at 1 and includes 1, and it goes up to infinity, okay? Alright, so when we have a relation in which the domain is not explicitly stated, so we're not told what the domain is, the domain is assumed to be the largest set of x values for which that relation is defined, okay? And this is called the implied domain. So over here, I just calculated the implied domain of that parabola. Okay, I haven't been told any different. I haven't been told I'm only drawing part of this parabola. Therefore, I assume that it exists for the largest possible set of values that I can draw it for. Okay, so if we think about this relation here, set of ordered pairs such that y is equal to 1 divided by x. So the y coordinate is 1 divided by the x coordinate in all of these ordered pairs. Has an implied domain of. Okay, so again, we want to think about the possible x values for this graph. Now, you can either think algebraically about that. There is a limit on the x values. I couldn't put every single x value into this rule, because if I put x equals 0 into this rule, I'd be dividing by 0. And so this function exists for all numbers except for at 0. Okay, so the way that we're going to write that, so our domain here is going to be all the real numbers except for 0. Now, we have to put the 0 in the curly brackets, because if we don't, we're trying to subtract a number from a set. Okay, they're not like things. It's like trying to subtract y from x. They don't collect together. You can't actually do that. Okay, it's like apples and oranges. So we need to subtract a set from the set of real numbers minus the set of numbers that includes 0. Okay. So you can also do this thinking about your graph, okay? So that's the graph y equals 1 on x, that's a hyperbola. Okay, so again, thinking about graphically, all right, well, I can see my graph exists everywhere except at this asymptote here when x equals 0. And so the domain, therefore, the graph exists for all real numbers except for when x equals 0. Okay, so let's think that through for some other relations. So the first relation here is simply a list of ordered pairs. So the domain is going to be the list of all the x coordinates in those ordered pairs, and the range is going to be the list of all of the y coordinates in those ordered pairs. So let's list our x coordinates in order, 0, 1, 3 and 4. Yep, they're in order. 0, 1, 3 and 4 will be the domain, and the range will be all the y values, -2, 0, 1 and 3, they are also in order. Okay, then let's think about the next one. So set of ordered pairs such that y equals 4 minus 2x. Okay, so that's a linear function. It's a linear function with a y-intercept at 4 and a gradient of -2. It's going to look something like that. Okay, so thinking about the x values for which that graph exists. So that line goes on and on and on forever. When x equals positive 10 billion, I could calculate the y value, and when x equals negative 10 billion, I could calculate the y value. And obviously I could go further than that. So in terms of x values, this graph exists for all x values. So the domain is R, okay? The range, again, the line goes on and on forever. So any y value, you could substitute any value in here for y and calculate an x value, okay? It exists for all y values, and this would be true for all linear functions. A linear graph goes on and on forever, both horizontally and vertically, and so exists for all x values and for all y values. Okay, let's think about this one. So the set of ordered pairs such that y is equal to the square root of x minus 3. Now, being familiar with your gallery of graphs functions is really important here. We're going to need those quite a lot throughout this chapter. So this is a square root graph, and the minus 3 here is translating that graph to the right by 3. So it's a square root graph to the right by 3. Okay. So thinking about the x values where that graph exists, well, it doesn't exist anywhere to the left of x equals 3. It starts at 3 and it exists when x equals 3, okay? And then it exists for all x values bigger than that, okay? So we want the interval from 3, including 3, up to infinity would be my domain. You can also calculate that algebraically with the square root graph, and we'll talk a bit more about this later on, but you can also think about what x values does this function exist for. So the restriction here is the square root. This will only exist if what's under the square root is bigger than or equal to 0, because you can't square root a negative number. So that means that x is bigger than or equal to 3, which marries with what we've calculated up here, which marries with what we're seeing in our graph over here. Okay, x has to be bigger than or equal to 3. The domain is 3 to infinity. Okay, thinking about range. So range is the y values, so that we can see that the graph doesn't exist down here under the x-axis at all. It starts here on the x-axis and then it goes up. Now, square root graphs don't have asymptotes. Some of you have been tempted to draw them with some asymptotes. There's no asymptote here. This graph is getting bigger and bigger. Remember, it's a sideways parabola. Keeps going forever. Slowly, but it's still increasing. So its range starts at 0, including 0, and goes up to infinity. Okay, so then we've got y equals, so here we've lost the formal set notation. It's still a relation, we just lack, the rule still essentially just describes a set of coordinates, but it doesn't always need to be written with the curly brackets and the, in fact, you've been seeing plenty of relations like this up until this point. So we're looking at y equals x squared plus 5. So this is similar to the example we drew over here with our parabola earlier. So x squared plus 5 is a parabola translated up by 5. Okay, so again, like the parabola we drew previously, in terms of x values, there's no limitation on what x value we could sub in here. We could solve this. We could substitute any x value in, so the possible x values are unlimited, so all the real numbers is the domain. The range, clearly my graph, the lowest point of my graph is at 5, the lowest y value is 5, and then it keeps going up there. So the range will be from 5, including 5, up to infinity. Alright, let's think about this one. Y squared plus x squared equals 4. Now again, if thinking back to your gallery of graphs, this is a graph of a circle. It's a circle with its centre at the origin and with a radius of 2. And so therefore, the domain of this graph only goes from -2 up to 2, thinking about x values. Okay, there's no circle out here, there's no circle out here. So it exists at x equals 2 and it exists at x equals -2. So it's the interval from -2, including -2, up to 2, including 2. And then thinking about range, same idea. It exists only between -2 and 2. There's no circle up here, there's no circle down here. So our range is just going to be, from -2 to 2 as well. Sorry, deleted that y-axis 3 times. Okay, so range is also -2 to 2 inclusive. Alright, and then this one here, y equals 1 over x plus 2 plus 3. So this is a hyperbola. Now again, you really need to know your graph shapes here. So this is to the left by 2 and up by 3. So you've got asymptotes at y equals 3 and at x equals -2, and your graph has not been reflected, so it's happening here and here. So in terms of x values for which this graph exists, it exists everywhere except at that asymptote when x equals -2. So the domain here is all the real numbers except for -2, remembering that that number we want to exclude has to be in set notation, so it must be in the curly brackets. In terms of range, we've got the same thing. So the graph goes on and on and on forever up here. It gets closer and closer and closer to that line. On and on forever down here, down to -infinity. It gets closer and closer to that line. The only place where it doesn't actually exist is on that line at y equals 3. Okay, so therefore, my range is all the real numbers except for 3. So being able to think about the graph is going to enable you to state the domain and the range. Okay, so you need to know your graphs, so you know what it looks like, so you can decide what the domain and the range is, and then you also need to know your set notation from last lesson so that you can accurately describe the domain and the range using that set notation. Okay, so a relation can be represented on a graph. On a set of Cartesian axes. Okay, so as we said right at the beginning, anything we can draw on the Cartesian plane is a relation. So we could sketch the graph. Alright, so sketch the graph of this relation and state its range. Okay, so we've got set of ordered pairs. Okay, so that's just telling us it's a relation that follow this rule, y equals 2x minus 1, but only for these x values, when x equals -2, -1, 0, and 2. Sorry, -2, -1, 0, 1, and 2. Okay, so if we were just sketching y equals 2x minus 1, okay, well that's a linear graph with a y-intercept at -1 and a gradient of 2. X-intercept, calculating in my head, is at half. Okay, so that would be that graph without any restriction whatsoever. But we're not drawing that graph. Sorry, I should have used a different axis, given what I'm about to do. Just give me 1 second. Let's just draw that axis a little bit better than that. Ooh, sorry, dropped my pen on the screen. Okay. Alright, so let's say we've got half, 0, and 0, -1. Now actually, we're not interested in the whole line. We're only interested in this linear relationship where x is equal to -2, or where x is equal to -1, or where x is equal to 0, or where x is equal to 1, or where x equals 2. Okay, so by drawing a line, I'm drawing infinitely many points, where actually I only need to draw 5 points. Okay, so I've already got one of them drawn. Actually, we don't need that one, so we don't need that x-intercept. So I'm just going to see if I can delete that without, deleting my axis. Okay, so this is one of those points. That's the point when x equals 0, 0, -1. So let's do the positive ones. When x equals 1, y will be 2 minus 1, so that will be 1. I'm just thinking, again, I've got my scale a bit out. Sorry, just going to move that axis down a bit. Alright, so let's make that 0, 1. Then we will have, so we're going to have 1 and 2, and 1, -1 and -2. So when x equals 1, y equals 2 minus 1, which is 1. When x equals 2, 2 times 2 is 4, minus 1 is 3. Okay, so 1, 2, 3. Right, when x equals -1, 2 times -1 is -2, minus 1 is minus 3. And when x equals -2, 2 times -2 is -4, minus 1 is -5. And so that is the graph of that relation. Okay, it's not the whole line, it's a line with a restricted domain, and that domain is actually only specifying 5 particular points on that line, not the infinitely many points on the line. Alright, then we think about example 3, sketch the relation. Here we've got the same rule, but again, different domain. Sketch the graph of the relation, so set of ordered pairs where y is equal to 2x minus 1, so it's the same line, but only where x is bigger than 0, and state its range. Oh, sorry, did I miss that in the previous one? And state its range. Okay, sorry. So range here is the set of all the y values, which we can see from our points, -5, -3, sorry, that should be -1, -1, 1, and 3 is my range. Okay, so same idea again here. We've got the graph. It goes through 1, 2, 0, and it goes through 0, -1. Okay. But we're not interested in all of it. We only want the bit where x is bigger than 0. Okay, so x is, sorry, not bigger than or equal to even. X is bigger than, so it doesn't include 0, but all this way. So we only want the bit of the graph happening over here. Okay, so therefore, sorry, let me just get rid of that. We don't want this bit back here. We only want, oh, sorry. Having trouble negotiating my razor. We only want the graph to start at the y-intercept, but that point's not included. So on our graph, we're going to indicate that with an open circle. Doesn't include that point 0, -1. It's still important to mark that point because that's still an endpoint because the line exists all the way up to that point, 0.00000001. Okay, so this doesn't mean you start the graph when x equals 1. Okay, the next number after 0 is 0.0000, go on forever with zeros 1. Okay. Alright, so we don't want to include that y-intercept, we still mark it, x-intercept is marked, and so there is the graph of that particular relation. Okay, question 4. Sketch the graph of the relation. Oh, we forgot to state the range again, sorry. So the range up here, the range of this relation is going to be -1 is the lowest value, but it's not included, and all the way up to infinity in terms of y values. Sketch the graph of the relation and state its range. Okay, so this is a truncus. Okay, squared on the denominator, fraction with the x in the denominator, and the denominator squared. So it's a truncus. So we have a truncus. The negative out the front is reflecting in the x-axis. Okay, so that means we're going to get an elephant trunk truncus rather than a tree trunk truncus. The -3 in here is a translation to the right by 3, which means we'll have an asymptote when x equals 3. And we've also got a translation, this one here, up by 4, which means that we'll have an asymptote when y equals 4. Okay, so we want to sketch the graph. Remembering with the truncus and the hyperbola, you want to draw your asymptotes in first. They give you structure. Sorry. Okay, so asymptotes, dashed lines labelled with equations. I made a number of comments on your homework submissions around the hyperbolas and truncuses, where you weren't labelling asymptotes with equations, you weren't labelling all the required intercepts. Okay, many of you were drawing graphs that would literally be worth no marks in a test. Okay, so please make sure that you approach your homework graphs with the same level of accuracy that you would expect to deliver in a test where you'll need to do it. Okay, so our truncus is going to cross the x-axis somewhere here and x-axis either side of the vertical asymptote and the y-axis somewhere up here. Okay, so let's, sorry, again, unruly eraser. Okay, so let's calculate those points so we can draw the graph. So the y-intercept, we let x equal 0, so y is going to be negative. That'll be -3 squared plus 4, so that's -1/9 plus 4. 4 is 36/9. -1/9 plus 36/9 is 35/9. So it's just 1/9 less than 4, so pretty close to the asymptote. X-intercepts, we let y equal 0. Sorry, y equals 0. So we get -1 over x minus 3 squared plus 4. Now, yes, you could subtract 4 from both sides, but then you'll have negatives on both sides, so let's instead add the fraction. So we're going to get x minus 1 on x minus 3 all squared equals 4. Okay, multiply by that bracket to get rid of fraction, divide by 4, take the square root, which is where you're going to get your plus minus, which is how you get 2 x-intercepts, plus minus square root of a quarter, which is plus minus a half. Square root of 1 is 1 and square root of 4 is 2. And so x is going to be 3 plus or minus a half. Plus or minus a half, sorry. So 3 plus a half is 3.5 or 7 on 2. 3 minus a half is 2.5 or 5 on 2. Okay, so in terms of our graph, let's sort of roughly, so it's going to be about there, our intercepts. And quite close up to this asymptote here, it's only a 1/9 below it. Okay, labelling our intercepts, 7 on 2, 0, 5 on 2, 0, 0, 35 on 9. So again, intercepts were missing from a lot of your homework graphs. Okay, so that's the first part of the question. Sketch the graph and state its range. Okay, so the range here, y values for which this graph exists. Okay, so the truncus doesn't go up here at all. Okay, it doesn't go above the asymptote, and it doesn't actually touch the asymptote, but it keeps going down here forever. So that tells us about our range. Our range goes from negative infinity up to 4, but not including 4. That's an asymptote. It never actually reaches that value. Okay, number 5, last one. Sketch the graph of the relation and state its range. Okay, so again, we've got a set of ordered pairs, so it's just telling us the relation. This is the rule, and we're going to sketch it over these x values, so that's the domain. Okay, so my rule is 2x squared minus 6x, so it's a quadratic equation, so therefore the graph will be a parabola. Factorising 2x is a common factor there. I can see from that I'm going to have x-intercepts when x equals 0 and 3. Okay. My y-intercept will also be at 0. If you've got an x-intercept at the origin, that's automatically the y-intercept. We probably need the turning point in sketching the graph. We certainly need the turning point in thinking about the range. So if I just do a rough sketch here now of the graph, just to give you a sense of what's happening, you've got a happy parabola, so positive x squared term, with intercepts at 0 and 3. And so therefore thinking about the range of this parabola is going to require us to know about the minimum value, which is at the turning point. So we're going to need to calculate the turning point. Now the turning point clearly happens halfway between the intercepts, so the x value of the turning point is 3 on 2. Okay, so the turning point is when x equals 3 on 2, which is halfway between 0 and 3. So we can find the y value of the turning point by subbing 3 on 2 into our equation. Okay, so that is 2 times 9 on 4 minus 6 times 1.5, or 6 times 3 over 2. Cancelling the 6 and the 2 down, essentially get 3 and 3, so it's 9. Try not to have to go to minus 18 on 2 there and then simplify to 9. You shouldn't be multiplying the 6 by 3 at all. You should be cancelling the 6 with the 2. Okay, so that it's then just becomes 3 times 3, which is 9. Alright, so 2 times 9 on 4 is 9 on 2 minus 9, which actually in this instance we need the common denominator, so yes, it's 18 on 2, and so negative 9 on 2. Alright, so 3 on 2, negative 9 on 2. So there's my graph drawn. Again, intercepts, turning points, they're key features of the parabola, and all need to be marked and labelled. Okay, so the range of this particular relation is negative 9 on 2 and includes that point. The graph actually goes through that point, so, sorry, square bracket. So it goes from negative 9 on 2 up to infinity in terms of the y values. Okay, so there's some work there for you to do from exercise 5b, exploring this idea of domain and range and relation.